Yes, welcome back to Easy Gates Biomedical Gate 22 paper solutions. The next problem is also from analog electronics, but by using an ideal op amp. Okay, and this is relatively easy, and probably the biomedical aspirants got the solution instantly as compared to the previous 2 or 3 problems. They are relatively not tough, okay, relatively time consuming. That's all I can say. It's easy only. Okay, you should know the fundamental of DC analysis, AC analysis. You can compete. Okay, the problems we have done already. Okay, yes, let us get into this problem. So we have an ideal op amp with infinite gain, that's by default, even if it is not mentioned. Infinite bandwidth, that's also by default, is connected in feedback as shown below. The output voltage V0 for the given input voltages in the circuit is. So what is your output V0? Accurate to 1 decimal places. Okay, so 1 decimal place. Okay, so we need to find out only V0. So in the last 2 or 3 problems, we are finding V0 only. Okay, so earlier we played with op amp circuit and NMOS and also BJT. So focused on V0. This is also the V0 only. Okay, yes. So how to play for this? So this is having two kind of feedback. One is a negative feedback. This is offering a negative feedback, and this is offering a positive feedback. Okay, that's a very interesting problem. So we have seen already many applications. Okay, so using op amp, having only negative feedback, having only positive feedback. Only negative feedback means it's a linear application. Only positive feedback means it's a non-linear application. In linear application, V0 can stay between your +10 and -10 given VCC. Okay. If it is a nonlinear application, then by default, the output will be either saturated to +10 or saturated to -10. That's all. Only 2-level output possible if it is only positive feedback or no feedback. Okay, op amp will be always in saturation in any one of the 2 levels. So in this case, the circuit is exploiting both negative feedback and positive feedback. So by assuming negative feedback still dominates, let us go by the virtual short. The important concept that will help us to perform a rapid circuit analysis in any analog electronics op amp based problem. Okay, so let me go by VD equal to 0. Assuming negative feedback dominates. Okay, we'll try to prove it little later. Assuming negative feedback is dominating, then let us go with VD equal to 0. Once again, that's a virtual short concept. Okay, now this point is given. So this is 0. So this is going to be 1 volt. This is 0. Therefore, this is going to be 0.1 volt. Okay, now there is no current at the input terminals of op amps 0 and 0. If that is the case, what is this point potential? V0. What is this point potential? 1. Let me go for V plus. So what is V plus? Potential at the non-inverting terminal. What is that? You also call it as VP, positive terminal potential. What is that VP? So it is a voltage across. So there is a current in this. So find out this current I, and that current is going to make a drop across 1K. That drop plus 1 volt. Okay, so that means I can say what is the current in this? V0 minus 1 volt divided by total resistance will be the current in this branch. Okay, because there is no current in the non-inverting terminal. Then that is going to make a drop with what? 1K. That drop is going to be, this is plus, this is minus because of this direction of current. Added with 1 will be this 1 volt plus this drop will be this point potential. So plus 1 volt. Okay. Yes, you have to be a little careful at this point. Okay. So that's a equation for the VP. And similarly, we'll derive one more equation for the inverting terminal, call it as VN. Okay, the inverting terminal current is also equal to 0. Same way you find this. So this point is going to be V0. If that is the case, what is VN? VN is equal to V0 minus, we'll find out that branch current V0 minus 0.1 divided by the total resistance 2K plus 1K, that is going to be 3K. That's a current in this, and then find the drop across 1K, that is going to be plus minus as per the current direction. You call this as current I1. So this is your I1 into 1K, and this is your I2, and I2 into this 1K plus this 0.1. Okay, so into 1 kilo ohm, that's a drop across this 1K plus 0.1 volt. Okay, that's your VN. And given already VD equal to 0, since VD equal to 0, since virtual short is still there, assuming negative feedback is dominating, VP and VN cannot be different. So VP is equal to VN is a point to complete the problem. Okay. Yes, once you strike this point strikes, then you know the flow for the problem. So then what is the equation? VP is function of V0. VN is also function of V0. And then you're going to form an equation only function of V0. Then you can easily solve it. Yes, let us take the two equations. So the first one is V0 minus 1 by 6K, V0 minus 1 by 6. Let me take plus because it's 1K by 6K plus 1. Okay, plus 1. Okay, it's a voltage. Right hand side, it's V0 minus 0.1 by 3. So V0 minus 0.1 by 3 plus 1 plus 0.1. Okay, plus 0.1. That's all. Plus 0.1. So then what we get as a resultant? So I can take this as V0 minus 1 plus 6 divided by 6. Right hand side, V0 minus 0.1 divided by, okay, so it is going to be plus 0.3 divided by 3. Let me take, after taking LCM, V0 minus 0.1, so 3 into 0.1, it is 0.3. That's fine. Okay, then I can either cross multiply, otherwise better. This is going to be 2. Okay, 6. Okay, then over to the left hand side, V0 minus, the numerator is going to become V0 plus 5. That is equal to, multiply this by 2. So I'll get 2 V0. Then the 0.1 and 0.3 will become 0.2. So 2 times 0.2 is going to become 0.4. Okay. So the result is going to be, so I'll write 2 V0 minus V0, that is equal to, I'm pushing V0 this side, 0.4 this side. So 5 minus 0.4 volt. So then it is going to be V0. V0 is equal to 5 minus 0.4. That is going to be 4.6 volt. Okay. So that's what we are getting. We have to verify this. Okay. That's very important. Any circuit analysis needs a due verification because we might have committed some mistake somewhere. Okay. So the verification will help us to troubleshoot that. Okay. So to find it and correct it. Yes, V not equal to 4.6. Let me have a copy of this. Yes, we'll do the verification now. So the V naught we have determined is 4.6. So we have 4.6 volt. So then this is also going to be 4.6 volt. Okay, so this is also 4.6 volt. And this point already known as 1 volt. So now the current is going to be, this is higher potential, this is lower potential. The net drop is going to be 3.6. So 3.6 volt across this, that is going to be the current I1. Let me go for that current I1. It is 3.6 by 6 volt by kilo ohm. It is going to be 0.6 milliamps. Okay, 3.6 by 6. Okay, 0.6 milliamps current coming here will make a drop across this as how much? So 0.6 into 1K, it is going to be 0.6 volt. Okay, so 0.6 means this point is going to be at 1.6 volt. Okay, I need to do the verification now. So let me exploit virtual short. Therefore, the 1.6 volt will be here. It is 1.6 and this is how much? 0.1. If that is the case, the drop, because this must be on higher potential, this lower, the drop is 1.5 volt. Therefore, this current must be equal to 1.5 milliamps. So if I reflect this VP to the VN, that is because of a virtual short. So the current in this branch should be equal to 1.5, mean this current should also be 1.5. That's verification. If it comes 1.5, you are right. Otherwise, there is a mistake. So what's the voltage across this? 1.6. This is 4.6. So the difference is going to be how much? 3. So 3 across 2K will make the current 1.5. That's perfectly all right. So that is your current. Okay. Yes, it's verified. So what of the V naught we have determined is absolutely fine. Okay. So that's answer. Answer is 4.6. Up to how many decimal places we need to give? Up to 1 decimal place. So the answer is 4.6. That's relatively easy problem comparing to the problems I have already addressed. And hope you enjoyed this content. Subscribe the channel and also share to your friends. Okay. We'll update you with the next problem.